Chapter 3 Motion. How long can you stand perfectly still? 10 seconds? A minute? Even if you stand still, things inside your body are moving, like your heart and lungs. And even fast asleep, your body is not really at rest with respect to the universe. The 24-hour rotation of Earth is carrying you around at several hundred miles per hour. Every 365 days, Earth completes a 584 million mile circle around the Sun. To make this trip, you are rushing through space at the astounding speed of 60,000 miles per hour. Things are always moving. To understand nature, we need to think about motion. How do we describe going from here to there? Whether it's a toy car rolling down a ramp or the Earth rushing through space, the ideas in this chapter apply to all motion. Position, speed, and acceleration are basic ideas we need in order to understand the physical world. And velocity. Motion is about knowing where things are and how they move. The ideas of position, speed, and acceleration apply to cars, bicycles, and many other familiar things around you. These ideas also apply to the tiny atoms inside matter and to the planets and stars. We start our discussion of motion with a precise method to describe where things are. You may do an experiment in your class that uses a car on a ramp. How do you tell someone exactly where the car is? The answer is by measuring its position. Position is a variable. The position of the car is where it is relative to where it started. In the diagram below, the position of the car is 50 centimeters. That means the center of the car is at the 50 centimeter mark on the ramp. Position and distance are similar but not the same. Both use units of length. However, position is given relative to an origin. The origin is the place where position is 0. Here's an example of the difference between position and distance. Suppose the car moves 20 centimeters. Where is it now? You know the distance 20 centimeters, but you still don't know where the car is. Saying the car is at 20 centimeter mark tells you where the car is. The position of 20 centimeters on the ramp is a distance of 20 centimeters in front of or to the right of the origin of the scale of the ramp, figure 3.1, and backward. Some variables, like distance, can have only positive values. The distance between two of the ants in figure 3.2 can only be positive or 0. Position is different. Like distance, position is measured in units of length, meters, inches, etc. The difference is that you can be in front of the origin or behind it. How can you tell the difference between 1 meter in front of the origin and 1 meter behind the origin? The answer is to use positive and negative number. Positive numbers are for positions to the right, in front of the origin, and negative numbers are positioned to the left or behind the origin. Many variables can be positive or negative. These include position, speed, force. These variables are called vectors because they can have a direction as well as a value. When the only directions are forward and backward, using positive and negative numbers is enough information. When up, down, and right, left are also possible directions, vectors get more complicated. Motion can be going right or left, forward or backward. We use the term velocity to mean speed with direction. Velocity is positive when moving to the right or forward. Velocity is negative when moving to the left or backward. In conversation, you might use speed and velocity to mean the same thing. In science, they are related but different. Speed is a positive number value that tells you how many meters you go for each second. Velocity is a speed and a positive or negative sign for information that tells you whether you are going forward or backward. Velocity is a vector, speed is not. Pathfinder is a small robot sent to Mars, figure 3.4. As it moves, Pathfinder needs to keep track of its position. How does Pathfinder know where it is? It keeps track of its velocity vector and uses a clock. Suppose Pathfinder moves forward at 0.2 meters per second for 10 seconds. Its velocity is plus 2.2 meters per second. In 10 seconds, its position changes by plus 2 meters. In other words, Pathfinder is 2 meters in front of where it was. The change in position is velocity times time, figure 3.5. This is just like saying distance is speed times time. Only we're using velocity and position instead of speed and distance. We all use velocity instead of speed to include direction of motion. Now, suppose Pathfinder goes backward at 0.2 meters per second for 4 seconds. Where is it now? we can use the same relationship. Change in position equals velocity times time. This time the velocity is negative 0.2 meters per second. The velocity is negative because Pathfinder is moving backward. The change in position is negative 0.8 meters. The computer in Pathfinder adds up plus 2 meters and negative 0.8 meters to get plus 1.2 meters. After these two moves, Pathfinder is 1.2 meters in front of where it was. Pathfinder knows where it is by keeping track of each move it makes. It adds up each change in position using positive and negative numbers to come up with a final position. Pathfinder was crawling on a straight board. It would only have two choices for direction. Positive is forward and negative is backward. Out on the surface of Mars, Pathfinder has more choices. It could turn and go sideways. The possible directions include north, east, south, and west, and anything in between. A flat surface is an example of two dimensions. We say two because it takes two number lines to describe every point. One common way to describe two dimensions is to use north, south as one number line or axis. Positive positions are north of the origin. Negative positions are south of the origin. The other axis goes west-east. Negative position on the axis are west of the origin. Positive positions are east. Pathfinder's exact position can be described with two numbers. These numbers are called coordinates. The graph left shows Pathfinder at coordinates 4, 2. The first number gives the position on the east-west axis. Pathfinder is 4 meters east of the origin. The second number gives the position on the north-south axis. Pathfinder is 2 meters north of the origin. A graph using north-south and east-west axis can accurately show where Pathfinder is. The graph can also show any path Pathfinder takes, curved or straight. The kind of graph is called a map. You have surely used one before. Many street maps use letters on the north-south axis and numbers for the east-west. For example, the coordinates F4 identify the square that is in row F, column 4 of the map shown in figure 3A map. Suppose you run east for 10 seconds at a speed of 2 meters per second. Then you turn and run south at the same speed for 10 more seconds. Figure 3.9. Where are you compared to where you started? To get the answer, you figure out your east-west changes and your north-south changes separately. Your first movement has a velocity vector of plus 2 meters per second east-west. After 10 seconds, your change in position is plus 20 meters east. There are no more east-west changes because your second movement is north-south only. Your second movement has a vector velocity of negative 2 meters per second north-south. In 10 seconds, you move negative 20 meters. The negative sign means you move south. Now add up any east-west changes to get your final east-west position. Do the same for your north-south position. Your new position is 20 meters plus 20 meters and negative. Here and answer these questions.